Hello everyone. In today's lecture, we'll continue our journey with the time domain representation of LTI systems. And as you remember from the previous lecture, the objective was to find a relationship between the input and output of an LTI system, that is, a linear time invariant system. And as we have seen in the previous lectures, there were four methods of achieving such a relationship, and we started to focus on one of them, which is using the impulse response. And as you remember, the impulse response was basically the response or the output of an LTI system when the input is an impulse. And then we started talking about discrete time systems, that is, a system with an impulse response h of n and an input x of n and an output y of n. And using the linearity and time invariance property, we have showed that the output of such a system, y of n, is equal to the convolution between the input x of n and the impulse response h of n. So for any LTI system, the output will be the convolution between the input and the impulse response. And if you remember, the convolution was defined as follows. So y of n, which is the convolution between the input x of n and the impulse response h of n, is equal to summation of x of k times h of n minus k, summing over the dummy variable k from minus infinity to positive infinity, or equivalently summing h of k times x of n minus k and summing over the dummy variable k from minus infinity to positive infinity. This is the definition of the convolution, and if you remember, the steps to perform the convolution were as follows. We start by x of n and h of n. Then we replace the variable n with a dummy variable k. And then we choose one signal to keep as is, while the other one will be mirrored and then shifted. So if we choose x of k to be as is, and h of k will be mirrored, so h of minus k, and then time shifted h of n minus k. And then we multiply x of k times h of n minus k under the summation. Or equivalently, we can keep h of k as is, and then mirror h of minus k and shift. Then it will be x of n minus k, and now we can multiply h of k times x of n minus k and do the summation. This is basically these two definitions. And we have seen that we can compute the output of any LTI system through the convolution sum for discrete time systems. And we also have seen few examples. So let's start today's lecture with a new example, which is basically an LTI system described by this relation. Y of n minus rho times y of n minus 1 is equal to x of n. And the question is asking us to find the output from such a system given this input, assuming that b is not equal to rho and the system is causal. Before I start working in this example, let's discuss the causality of such a system. What does it imply? So going to our whiteboard over here, if you remember, when we describe a system to be causal, it means simply there is no dependence on the future. The causality simply means that no dependence on future. So this simply means that if we have an LTI system, the impulse response is basically the response of the system to an impulse applied at the input. If this is x of n, the input to the system, and it's equal to delta of n, an impulse at instant 0. So a causal system would start responding to such an input and creating an output y of n, which is h of n, the impulse response, starting from instant 0 and after that. So if the impulse response takes this form, now it's a causal system. But what would happen if the impulse response starts over here, before 0? If the impulse response starts over here, it means that the output started to appear before the input, as if the system has seen the future and knowing that there's an impulse coming at instant 0, it will start producing output before the input. So this impulse response, this red impulse response, is non-causal. Whereas this black response over here is causal. So for a system to be causal, the impulse response has to start at n equals to 0. So for a causal system, h of n, the impulse response, must be 0 for n less than 0. This is basically because for a causal system, the output happens after the input. It cannot start happening before the input. So let's go back to our question over here and start working on it. Y of n minus rho y of n minus 1 is equal to x of n. So let me write it like this. So it's y of n equal to x of n plus rho y of n minus 1. Okay, and the question is asking us to find the output for this input. So in order to achieve this output, we need first to find the impulse response of such a system, and then perform convolution between the impulse response h of n and the input x of n. One might suggest that we just plug in this x of n into this equation, which will give us y of n equal to this x of n, b to the power n u of n plus 4 minus rho times y of n minus 1. In this case, we do not have a closed form expression for y of n. We're looking for y of n equals this and that. We're not looking for a recursive equation where y of n is computed using y of n minus 1. So in order to achieve this kind of closed form relationship, we will first start finding the impulse response and then perform convolution. Going to our whiteboard over here, how can we find the impulse response? In order to find the impulse response, first we have to replace x of n by a delta of n. Because as you remember, the impulse response is the output coming out from a system when the input is an impulse. So the first step in order to get the impulse response is simply to apply an impulse to let x of n equal delta of n. And in this case, y of n will be replaced by h of n, and y of n minus 1 will be h of n minus 1, which is simply h of n will be equal to delta of n plus rho times h of n minus 1. And using this relation, we can find the impulse response as follows. Let's start with the time instant n equal to 0. So now we need to evaluate this equation at n equals 0. In order to do that, let me remind you of the impulse function. The impulse function is simply having the value of 1 at instant 0 and having the value of 0 as a rise. This is delta of n. So when I ask you for the value of this function, delta of n at instant 0, it's 1. And the value of this function, delta of n, for any other time instant, it's simply 0. So moving on, so at instant equal n equals 0, we will have h of 0 equal delta of n evaluated at instant 0, which is 1, plus rho times h of n minus 1. 0 minus 1 is minus 1. So here we need to find the value of h of minus 1. But if you remember, the condition of causality implies that h of n is equal to 0 for n less than 0. So for n minus 1, minus 2, minus 3, h of n is 0. So now we can easily write that h of minus 1 is equal to 0 due to the causality, which makes h of 0 equal to 1. Now, at instant n equal 1, we will get h of 1 equal to delta of n evaluated at instant 1. So this is the function delta of n. At instant 1, its value is 0. So at instant 1, the value here is 0, so we can move on over here and write 0 plus rho times h of n minus 1, which is h of 0. H of 0, we know it already from the previous step, it's equal to 1. So now we know h of 1 is equal to rho. Next, we can let n equal 2, and then we will get h of 2, it will be delta of n evaluated at instant 2. So the function delta of n at instant 2, it's 0. So we will be writing 0 plus rho times h of 1. But h of 1 is equal to rho. So this will be rho squared. Similarly, if we do for n equals 3, we will get h of 3, it will be rho cubed, and so on. So now we can come to the conclusion that at n equals 3, it's rho to the power 3. At n equals 2, it's rho to the power 2. At n equals 1, it's rho to the power 1. At n equals 0, it's rho to the power 0, which is 1. So now we can conclude that the impulse response h of n is equal to rho to the power n. But something is missing over here, because all of this is based on the causality property over here, which leads to h of n equal to 0 before n less than 0. So we need to multiply h of n by u of n. U of n, the unit step, will guarantee that h of n is equal to 0 for n less than 0. So the expression for the impulse response is h of n equals rho to the power n u of n. Now we are ready to perform the convolution sum and find the output. So going back to our example, we need to find the output for this input x of n equals b to the power n u of n plus 4. So the input x of n is b to the power n u of n plus 4. And as you remember, u of n plus 4 is a unit step that starts at minus 4. Unit step shifted to the left. So as usual, we will do the convolution graphically. So the first step is to draw x of k, which would be starting at minus 4 and would be right-sided, something like this. and it will be b to the power k u of n u of k plus 4. So it will be simply b to the power k u of k plus 4, which is already happening over here since we start from minus 4. And also we will need to plot h of k, which is rho to the power k times u of k. So it starts at 0 and then it will be rho to the power k. Next step, we'll choose one signal to keep as is and the other one to mirror and shift. I will choose to keep x of k as is, and I will mirror and shift h of k. So first step is to mirror and get h of minus k, which will be a mirrored signal like this, and it will be rho to the power minus k. And next we'll start shifting this signal h of n minus k such that this 0 will become n, and the expression will be rho to the power n minus k. Now if we start to change the value of n from minus infinity to positive infinity, we can get the convolution result. If n is less than minus 4, there will be no overlap and the result will be 0. If n is larger than or equal to minus 4, we will get some overlap from n equal to 4 up to n, from k equal 4 up to n. So we can write the following: y of n will be equal to 0 if n is less than minus 4. As you can see, if n is less than minus 4, there will be no overlap, and in this case the result will be 0. But if n is larger than or equal to minus 4, we will have a summation going from minus 4 up to n. So in this case, if n is larger than or equal to minus 4, we will have a summation over the variable k going from minus 4 up to n. And now we will be having x of k times h of n minus k. X of k is simply bk, and h of n minus k is rho to the power n minus k. So inside the summation we'll be having b to the power k rho to the power n minus k. Of course, this summation is over the variable k, so I can move rho to the power n outside of the summation. And now we will get the following. So y of n will be equal to rho to the power n summation over the variable k going from minus 4 up to n, and inside the summation we will be having b to the power k rho to the power minus k, which is b over rho to the power k. B over rho to the power k. And this summation is true as long as n is larger than minus 4, larger or equal to. But if n is less than minus 4, we will get a 0, which is equivalent to multiplying by unit step u of n plus 4. So this expression will be multiplied by u of n plus 4. Okay, the summations we know it basically starts at 0, but here summation starts at minus 4. So in order to take care of this, we will use a new variable. We will call it m, and we will let m to be equal to k plus 4. In this case, if k is equal to minus 4, m will be equal to 0, and if k is equal to n, then m will be n plus 4, and k will be replaced with m minus 4. So let me write this down. So y of n will be equal to rho to the power n summation over the new variable m going from 0, which is this one. When k is minus 4, the lower limit of the summation, it becomes m equal to 0. And when the upper summation is n, k equals n, m will be n plus 4. So now it will be from m equal to 0 to n plus 4. As for the term inside, the term inside was b over rho to the power k. Now it will be b over rho, and we will replace k with m minus 4. m minus 4 u of n plus 4. So now we will be having rho to the power n, and we can take b over rho to the power minus 4 outside the summation, and we will be having the summation right now m from 0 up to n plus 4 of b over rho to the power m u of n plus 4. And this summation is similar to one of the summations we have discussed in the previous lecture. Let's go back to the slides, and over here we have a summation r to the power n going from 0 to n minus 1, and in our problem r is b over rho. And now if this r is equal to 1, which is b equal to rho, the summation will be the upper limit of the summation plus 1. And if r is not equal to 1, which is in our case b is not equal to rho, it will take this form, 1 minus r in the denominator and 1 minus r to the power n in the numerator. So going back over here, we will be having two situations. If b is equal to rho, y of n will take this form. So we have rho to the power n, b over rho to the power minus 4, so rho to the power n, b over rho to the power minus 4. And this summation will be summing 1 plus 1 plus 1, since b is equal to rho, from 0 to n plus 4, which will give us n plus 5. Of course, multiplied by the unit step u of n plus 4. But if b is not equal to rho, in this case, we will be having y of n equal to rho to the power n, and then we'll be having a term b over rho to the power minus 4, and then this summation will be 1 minus b over rho in the denominator and 1 minus b over rho to the power n plus 5 in the numerator. Be like this: 1 minus b over rho in the denominator and 1 minus b over rho to the power n plus 5 in the numerator. Of course, multiplied with unit step u of n plus 4. So this would be the output for the given input. Moving back to our slides over here, let's take a look at the example one more time. So we were given the relation between y and x, and first we found the impulse response, and then we found the output for this input. So the first step is that since the system is causal, h of n will be 0 for n less than 0, that is the impulse response, cannot begin before the input, which is the impulse applied. And then we find the impulse response to be rho to the power n u of n. And then we start doing the convolution, and we get the final result in the two cases. If b is equal to rho, it's rho to the power n plus 5. And if it's b not equal to rho, it will take this form. And here is a graphical representation of the convolution. This is x of k, this is h of k, h of minus k, h of n minus k, and now we can do the convolution. And this is the plot of the output y of n for a certain values of rho and b. I will not be asking you in the exam, to draw any function that's not easy to plot. So I will not ask you to plot something like this. If we go back to the whiteboard for a second, looking at this expression in the case for b equal to rho, of course we can note that we have this term b over rho to the power minus 4, which does not appear in the slides. If you go back to the slides, you will be having just rho to the power n, whereas here we have rho to the power n times b over rho. Of course it is the same, because simply since b is equal to rho, this term will be equal to 1. So we'll end up with rho to the power n times n plus 5. Okay, so there are many solved examples in the textbook. I encourage you guys to try to solve them. These solved examples usually come with just the final answer or the detailed steps, it depends. But I want you guys to exercise as much as you can. Convolution is very straightforward, very easy, but it needs a lot of practice. Okay, in this example, we're asked to find the step response of a discrete time system in terms of its impulse response, h of n. So given the impulse response, h of n, we need to find the step response. Let's go to our whiteboard and see how we can solve this example. So basically we have an LTI system whose impulse response is h of n, and of course as usual the input is x of n and the output is y of n. And we need to find the step response, and the step response means simply that the input x of n is a unit step, and in this case the output y of n will be the step response, which we usually call S of n, the step response. So step response means simply the output coming out of the system for an input which is a unit step. So we'll be doing the convolution. So in order to find the step response, S of n is the convolution between the input, which is unit step in this case, and the impulse response h of n. I would choose to keep h of n as is, so I'll keep it h of k, and we'll do a mirror and shift for the unit step u of n minus k. This should go from k equals minus infinity to positive infinity. So in order to understand how to compute this summation, let's try to compute or try to plot first u of k. U of k is a unit step starting at 0 going up to positive infinity. This is u of k. Next we mirror u of k, it will be something like this, going from 0 up to minus infinity. This is u of minus k. And then we will start shifting this unit step such that this 0 becomes n, and this would be u of n minus k. So as we can see, u of n minus k starts from minus infinity up to n. So going back to our summation, this summation would be for k going from minus infinity up to n h of k. and this would be the step response in terms of the impulse response. So whatever the impulse response is, you do a summation from minus infinity up to n in order to get the step response S of n. Of course, if the system is causal, for causal systems, we know that h of n is equal to 0 for n less than 0. So if we go back to the summation we have, from minus infinity up to minus 1 will be 0. H of k is 0 for a k less than 0. So this summation will be from 0 up to n, h of k. So for a causal system, the step response S of n would be summation over k going from 0 up to n, h of k. So let's go back to our slides over here. So the step response is the output y of n when the applied input is a unit step u of n. So following the convolution, we can get S of n to be summation from minus infinity up to n of h of k. And of course, this is u of n minus k doing the convolution. We start with u of k, then u of minus k, then u of n minus k. And if the system is causal, if h of n is 0 for n less than 0, which is equivalent to a causal system, the summation would be from 0 up to n of h of k, instead of going from minus infinity up to n. And also from the linearity property, we can see that S of n minus S of n minus 1 is equal to h of n. In order to understand this equation, let's go to our whiteboard for a second. And we know that u of n minus u of n minus 1 would give us just one impulse at 0, which is delta of n. So applying delta of n to a linear time invariant system will give us the impulse response h of n. And the property of linearity implies that if an input is a summation or subtraction of two inputs, then the output would be the summation or subtraction of the corresponding outputs. So the output for the input u of n is the step response S of n, and the output for u of n minus 1 is a shifted step response. This is due to the time invariance property of the system, and since both of them are subtracted, we will subtract the two responses. Therefore, we can see the impulse response is a subtraction of the step response S of n minus time shifted step response S of n minus 1. This has happened due to the linearity property of the system. So the next example, we need to find the step response of a first order recursive system, that is rho to the power n u of n. So in order to get the step response in this case, we need just to apply the definition. So going to our whiteboard over here, the impulse response, the step response S of n for a causal system is a summation from k equal to 0 up to n of h of k. So how did I know that the system is causal? Because h of n is 0 for n less than 0, because we have u of n over here. So now we will be summing rho to the power k. So this would be summation of rho to the power k from k equal to 0 up to h. And this summation will be 1 minus rho, of course this is n, 1 minus rho to the power n plus 1. Of course, this will be true if n is larger than 0. But if n is less than 0, we will be summing terms that's basically 0. H of k is 0 for k less than 0. So we need to multiply this by u of n, and this would be the step response of this system. So it will be 1 minus rho in the denominator, 1 minus rho to the power n plus 1 in the numerator times u of n. And now we have concluded the discrete time convolutions, the convolution sum. In the next week's lecture, we will start talking about continuous time systems and the so-called convolution integral.